Hello, and thank you for the introduction. I wanted to start with this story as well. I'm a computer science student here at KIT, and as balance for the more theoretic studies, I am part of a local CTF team called Kids CTF, and I gather working experience at a local company with, for example, pen tests. And with the CTF team, we annually host a CTF competition. The edition of this year is running as I speak. And for last year's edition, a friend of mine gave me a challenge to playtest for this competition to reverse engineer and test how it's working. And so, given a binary that I didn't know, I tried to find more information about it. And file is usually a good starting point to get this information, but in this case, it was missing the CPU architecture in the middle where it says unknown arc. Usually these are assigned machine values that say which CPU we are dealing with, and this one was unknown. But the value is one we can search for, and it just turns out that it's a rarely used and very old compiler for a tiny C compiler that is shipped with well-grind perf. And so now we know that it's just the same architecture as the architecture actually has a machine value, but maybe not when this compiler was written. So now that we know what we are dealing with, we can look up the documentation for this architecture, and we could start analyzing the binary in earnest. And at first I searched for a disassembler that worked for this architecture. This is the output from lib opcodes, which is shipped with object dump. And we could have, now we have a structured output that we could analyze manually, or today probably also give it to an AI, but we don't want to do that. We want to understand what we are dealing with, and we want to automate the process and have a structured approach. And for this, we will use a decompiler. A decompiler aims to reverse the work of a compiler, in that it tries to recover higher level structures like loops and functions again, and it tries to recover a result that is close to the original source code, but as the compiling process removes information, the result we get will also be only close, and there will be losses in the process. Our decompiler is like an IDE for reverse engineering, as we can name functions, we can create types, and track our changes as we go. To work with a decompiler, we need a basic architecture support, because high-level analysis is independent of the architecture and the binary type. But the first step needs information about the architecture, and that is what we try to solve with an architecture plugin using the API of the tool, in this case Binary Ninja, to support the new architecture. This support was missing initially. And before we talk about how this is usually done, one look back at the original binary that I was dealing with. We hosted the competition, and we made a mistake with deploying it. And in case you are not aware, this is the solution for the challenge, so people could just find it as a string, and I believe nobody really looked at the architecture in detail, but we will now. So, if we want to build a decompiler plugin with Binary Ninja, maybe start with some information about Binary Ninja. This is a commercial product, and I will talk about the plugin. If you want to use a plugin with Binary Ninja, you need any paid license. I'm not sponsored by Vector 35. If I present any opinions, they are my own. I chose Binary Ninja despite that because I wanted to learn how to use the tool better, and it has a rather stable API. There are several APIs we can choose from. One of them is in C++ as the tool is written in. Another one is in Python, that's the one I chose. And there's also one in Rust that is currently in development and maybe unstable. Python gives us short development cycles, and we can start with a very short part to get our plugin rolling. And every part we build needs to be registered with the tool on startup, so we add our architecture first. Our architecture is the core of our plugin, and we start by adding general information about the architecture in the plugin. This includes, for example, the name that is displayed everywhere, but also general information like how large is every address, or my instructions, how are they aligned. Some of these informations you see below. We also tell the decompiler about the registers. That information we can later use during lifting. Every register we define now we can later use. And then our plugin has 3 core tasks to provide higher level information in the end. The first task is we want to recover control flow. That means we want to discover functions and split them up into basic blocks and branches between them. And the second part is disassembly. We already saw disassembly, but we want to provide that in a way that Binary Ninja can work with. And the third part is lifting. That's where the magic comes in, I guess. It's the information that we give to Binary Ninja about what every instruction does, so Binary Ninja can then start its analysis. We need a disassembler for every task, so I guess we can always search for one and use it as dependency. In my case, I wrote a Python one where I could control the API, and then we can use that as a basis for the results we need for control flow, disassembly, and lifting. And every of these tasks assumes that we usually deal with one instruction at a time, or a few instructions at a time, and process them separately. So the first task in detail would be recovering control flow. That's one function we need to implement. We get data and address, so we can disassemble our instruction, or we need to disassemble our instruction first, and then we want to return information in an instruction info object. This includes the actual size of our instruction as well as branch information. Branch information is a branch type. If we know it, the branch target might not be known at that point because it might be a relative target. And we can also provide an architecture. ARM architectures have multiple sub-architectures where they can branch between. And then there's a delay as well. This is an instruction delay, so if we have a delayed branch, we can specify the instructions by that it is delayed. And this result we pass back to Binary Ninja, and it has a default basic block analysis algorithm that usually already recovers all basic blocks correctly if we use the correct branch types and our architecture is somewhat compatible with this approach that they use. In our case, we can try that and it would work for the tiny C binary that we had in the beginning, but it wouldn't work for more complex ones. The details why we have problems I will explain when I talk more about the architecture soon. Let's first talk about the second task. Usually, to provide disassembly, we just need to translate the disassembly that we already have into a disassembly language tokens that Binary Ninja can use. This is just translating from one output to the other in a structured way that Binary Ninja can provide highlights and search and other more interactive navigation with the information we provided. Here's one example for an opcode token that we will need for every instruction. And it could highlight the opcode with that. It's pretty straightforward, and this is the part that works best with this architecture as well. And then there's the last part, lifting. The usual lifting approach is we get our instruction and a low-level IL function, and we add IL instructions, intermediate language instructions, to this function. We do this by translating our instruction into this intermediate language. Just a bit more context, Binary Ninja has multiple intermediate languages, ranging from low level to medium to high level. And each of these also have multiple different steps in between, because Binary Ninja translates between them when analyzing to reduce unused code and so on. We have to only have to provide the first step, that is the low-level IL, and Binary Ninja can then go on. It's a tree-based custom language with rather simple instructions. For example, set register is one instruction in this language, and then it would have one operand, meaning the value that we assign to it. And each operand can always be another IL instruction, so we have a tree, in this case, an add with 2 more operands. This would be a translation of decreasing the value by 1. The major issue we have, the major problems we will have is with lifting, because most of the specifics of the architecture result in problems with lifting. So what is the architecture we are talking about? This is the name, TMS320C6x, a long one. I will only abbreviate it in the future as C6x architecture. It's a DSP architecture by Texas Instruments. So digital signal processing, it's intended for audio and radar applications. And it is meant to be very performant on a dedicated set of use cases, for example, for multiply and accumulate loops. It's a 32-bit RISC architecture, so addresses are 32 bits, registers are 32 bits, and instructions as well. It's a load store architecture, and we have 2 register files of either 16 or 32 registers. In the base version it's 16, and in later updates they increased it to 31 registers. There are 8 functional units, 4 of them are shown in the bottom, as well as with the wires they connect. They have dedicated usage. For example, the M unit you see there is for multiplying, and the D unit would be for load and store operations. As you can see, every of these units can always access its own register file and write back to it, but we can only read from, every cycle we can only read a few values from the other register file, otherwise we would have wiring conflicts. So that's already one hint. The architecture needs a compiler that is highly optimizing for this architecture, otherwise it's no use. And that's also why the tiny C compiler is not really interesting in this case, because it didn't optimize at all. This is a very long instruction word architecture. We have 32-bit instructions, but they are usually grouped into a group of 8 instructions. We had 8 functional units, and 8 instructions mean each cycle, each functional unit could be used. We load 8 instructions, and they could be executed. All of these functional units could execute in parallel. There's 2 of them for each type. And I've already said it's instruction level parallelism, meaning each cycle they could execute in parallel. And the 8 instructions that we load, I will call a fetch packet. We don't always have fully parallel execution, of course, because of data conflicts, wiring conflicts, and so on. But in coding, we already say which instructions will execute in parallel. That is decided at compile time. And the instructions that will actually execute in parallel are called an execution packet. So that's any subset of a fetch packet. And this is encoded by the least significant bit in each instruction. That is a parallel bit that says if it's 1, the next instruction is executed in parallel. So that also means the last bit should always be 0, because at this point it's only allowed to split up a fetch packet, not have parallel execution across multiple fetch packets. And below we see the syntax for parallel execution. So the instruction B would be executed in parallel. And we notate that with instruction B, but the information is actually stored with instruction A. This is the one part that doesn't work with disassembly tokens on the fly, because we only have the information with instruction A, and we would need to output it with instruction B. One more core feature of this instruction is that we provide that every information about how long an instruction executes is provided at compile time. And this is an overview for all the instructions. The important part is first the functional unit latency explains if we execute an instruction, how long will the functional unit be blocked. So one instruction is one cycle is the default, meaning we can execute something each cycle, but more complex instructions will block the unit longer. Then there's read and write cycles, and the annoying thing is that they are also across multiple cycles. For example, we often only read one register per cycle, and if we have instructions that need 4 registers or long register combinations, then we will have up to 4 cycles until every register is read. And the results might also take longer to compute or fetch. For example, the load instructions take 4 cycles until the value is read and written back to a register. And one more important thing, branches take 5 cycles of delay. That means that in the first cycle, we already calculate the branch target. Then we write it back to the first stage of the pipeline, and it simply takes 5 cycles until this pipeline reaches execution again, and we are at the new address of execution. This also means for us, when we translate things for control flow or lifting, that there can be 5 branches queued before the first one executes or applies. And in an optimizing compiler, that is somewhat problematic. One other cool feature that we can deal with is conditional execution. Nearly every instruction can be conditional. So it's not only conditional branches, but we could also say, for example, this is an instruction that sets the high half of one register. We had 32-bit registers and 32-bit instructions, so we need 2 instructions to fully set a register with immediate values. And this is one half of that, and it can be conditional. And most of these instructions reserve 4 of the 32 bits for encoding if it uses a condition and which condition it actually uses. There are the low registers are reserved as conditional registers, for example, B0 to B2, A1 and A2, and in later versions also A0. I've already mentioned versions a lot. There's a base version that just does fixed point execution, and the other versions are additions that are always backwards compatible, but add new features on top. And for example, the 64X versions are also fixed point DSPs, but they add more 8 and 16-bit arithmetics, non-aligned load stores. And one feature we will look at more in detail is compact instructions and software pipeline loops, because they also pose problems. Then there's the 67X versions, which are floating point instructions, and the plus version adds new registers, so we have these 32 registers per register file then. Also at that point, it changes that we can actually have parallel instructions across fetch packets, but that's not something we'll have to deal with here. The 674 version just merges two versions together again, and the last version we'll not discuss in detail. It would add vector processing. So one more thing we'll look at before we try to solve these problems is compact instructions. Up to this point, every instruction was 32-bit size, and then they decided that it would be good if the frequently used instructions would have half the size. So now we can encode instructions in 16-bit, and because all instruction formats were already used and there would have been collisions, they needed to find a way to encode which instructions are compact, and they decided to use the last instruction in each 8-instruction fetch packet to encode if this instruction has compact instructions, and we can detect that with the condition bits. This would be a reserved condition, so it's not used. And the other bits encode first as layout which instructions are actually compact, and then the p bits which of these compact instructions are parallel, and the expansion bits are shared information for each of these instructions. This is another challenge for translating it later, because we always need to know the 8th instruction of each fetch packet to even determine if we are dealing with compact instructions or not. And we need to process this information correctly to then decode each instruction. One last feature that I will just mention that it exists. This architecture also has support has hardware support for loops. So instead of encoding each branch and preparing, I mean, we have delayed branches of 5 cycles branch delay. So if we have a highly optimized loop, we would have to prepare a lot of branches and loads beforehand in the prologue to have a fully utilized loop in the end. Instead, we can use a small set of instructions, SP loop, SP kernel, and SP mask, and this hardware optimization. And then we have loops that operate in a loop buffer, and from the start of the loop, everything gets executed each cycle. The SP loop instruction tells us how many cycles we loop in each stage. And the SP kernel instruction ends the loop, and the SP mask instruction is for the middle if we have instructions that we don't actually want to store in the loop buffer. So now let's look at one of these highly optimized examples that we are doing this for. And this is a multiply and accumulate loop that they advertised as this is the cool thing we can do. This is a loop that executes 2 16-bit multiply and accumulates each cycle, and it uses all of the 8 functional units each cycle, and this is just the core loop. So with this version, we would have to add a prologue with queuing up branches and loads, because loads are delayed by 4 cycles and branches by 5, so this takes a bit to set up. And the other version with software pipeline loops, there the advantage now is that this is actually a complete example where we would set up the loop and just say the loop starts with the SP loop instruction, and it's 1 cycle looping. And then everything from the start of the loop would be executed each cycle, and when we reach the SP kernel instruction, then everything is looping, and we can say our loop ends here, and when the loop counter reaches 0, then we exit the loop and the loop buffer drains again. So how would we translate that? What are the problems we encountered? First, for control flow, we have branch delay that is in cycles, not in instructions. So we can't use the default branch delay that Binary Ninja provided. Also, we have multiple queued branches that breaks everything completely of the default algorithm. Then for disassembly, that mostly works, but parallel instruction and this SP loop instruction break two details. So that is something we want to fix. And then there's lifting, and we have parallel and delayed execution. And there the problem is, if we have multiple instructions in parallel, they always first read registers, then they compute, and then they write back their results. So even two instructions that just move one register to another, if we have two of these, and then we could swap registers, and that wouldn't work if we would just translate them one by one. And the second part is basic block boundaries, because if we split our function into basic blocks first, and then we have instructions that are delayed, and they are still pending when we reach the end of a basic block, then we need to handle conflicts that arise and decide if we want to translate them in the first basic block or somehow transfer them to the target. And all of these problems are somehow caused by the first design that each of these tasks should be solved by handling single instructions. And that's something that started to change with updates over the last year. So we now will look at how to solve these things. And the first update they provided for the API was an update where we can now change the default algorithm for analyzing basic blocks. And if we implement this, then we completely replace the default algorithm that Binary Ninja provided. They kindly open sourced their version, so we can just modify small parts if we want. But this gives us full control over basic block analysis. And we will do this on function level, so for a whole function at a time. We get the function as input, we get a context object with some additional information for doing this, and this also gives us access to the binary view, which is an object that gives us every information that is available about the current binary. And what we should return is a list of basic blocks and branches in between. And in the beginning we talked about instruction info that we generate with the default approach. Now we can use that or skip it if we want, because if we use it, then it's only used by us. If we replace the algorithm, no one else will use the instruction info. So if it's useful, you can use it, or you can just leave it out. How do we do basic block analysis? This is the important APIs gathered on a slide. Most of them are for handling basic blocks, and the obvious start is we want to be able to create basic blocks that start at a certain address. We also provide the architecture always, because there could be an architecture that has multiple subtypes, but for us it's always the same one. Then we want to add outgoing branches for each basic block. This takes a branch type, and that is also why the instruction info is not necessary strictly, because we pass the branch type there, and what we do with the branch type before, and if we actually use branch information before, is completely our choice then. Then we can also add instruction data. This is the fun part is that we should usually add instruction data, because the default algorithms use that sometimes, but sometimes they just don't, because they also have the binary, and sometimes they just decide to read from the binary instead. So if you add instruction data there, then you have to look up if it's actually used where you want to have it. I wanted to change the instruction data as a workaround before they added further API changes, and it just didn't reach the disassembly text function that I implemented. Then we also need to provide some additional information for each basic block. For example, this can exit attribute encodes that this basic block has edges that leave this block again. So if we have some exit or halting instruction, then we would set that to false. And one warning, this property is not read-only, but if you look at the documentation that it says it's read-only, because they show the documentation for the getter for this property, and there's also a setter, but they don't show the documentation for that. So you will find a lot of read-only properties. Don't let that confuse you. And another property that's also read-only that we actually need to set is the end of each basic block, the end address. If we don't set that, then Binary Ninja just crashes. And if we are finished, then we add the basic block to our function. And there's some utility APIs as well that we can use. As I already explained, that we can retrieve the binary view, which is the global view of the binary, from the function object that we get. And then we could, for example, read bytes from the file. Then the other two are information that we should respect and when we should abort our analysis, and when we are done, then we finalize our analysis with context finalize. So how could we do this for our C6x architecture? We would have to loop over every block, and for every block we would have to loop over every instruction. And we would do this in groups of cycles, meaning execute packets that actually execute in parallel. And then we take every branch of this execute packet and queue it up. They are delayed usually. The only exception is the SP loop. And each cycle we would also drain one cycle of the queued branches and apply these branches to our basic block. And then we have outgoing branches to other blocks and possibly other pending branches that are still in the queue. And we have to transfer these pending branches to other blocks to get a correct analysis result. One example for that is this. This is from a small example binary with the Texas Instruments compiler, so it's actually using the features of the architecture. And we get one block that only has an op. And that's actually correct analysis. But it's a bit confusing at first because it doesn't do anything in this block. But the reason we see on the right part, this is part of a larger loop, and we are queuing multiple branches. With the same condition, you see it's not B0, and there's B for branch and bnob for branch and wait, and then we have multiple targets. And this means that we first branch to this block with the knob, and then branch away again. The compiler does these things because there's multiple paths in this loop, and it wanted to optimize the hot path, and the hot path is not this knob path. So in the hot path, we want to only wait for 4 cycles, and if we want to return to the beginning of the loop, then we have one more cycle for branching away. So we spend this cycle in an extra basic block where we just wait. Another thing, also, we need to look at the conditions, because in the source block, we have twice the same condition, not be 0. So it's a conditional branch. But in the target branch, we only reach this branch if the condition was true. So we should translate that as unconditional, and then we get this the target block with an unconditional branch. This is something that's possible with the basic block analysis update. It gives us full control over this. Then we had a problem with disassembly text, and they improved this by adding another update, a small update in this case. I already said that the disassembly was pretty good already, but we couldn't translate multiple instructions at once because we just couldn't emit any new lines. So if we translate multiple instructions before that, then we either have all instructions in the same line or we have another problem. In my case, I just decided to have the parallel notation in the line before, and with new line tokens, we can now improve that. I'm mentioning this in a bit more detail here because my first attempt looked something like this, which is okay, I guess, but if you look at the details in the left, then the address and the hex dump are incorrect. So we would have line breaks, and the address for both instructions should be different, and the hex dump should also be split over 2 lines. Why is that? I didn't know how to use their API correctly, and it was not documented well, in my opinion. They have these optional parameters that I was not using at that time, and I was just using the token type, a new line, and text, no text in my case, and then it didn't work. Turns out I would have needed to use the value and assign the correct value. What is the correct value? Well, let's now look at a few sources that we would have for documentation. They do have a lot of sources, and some of them are actually written quite well, but if they don't have the details that we are looking for, and it was a new update, so there was information in the development API reference, but there was no blog post, no everything else. And turns out, if we don't find information, we can also take a look at the other APIs, because some of them are written a bit differently, and this gives us more information. And in this case, the Rust API is quite helpful. As I found out, the Rust API actually tells us how these values are used, if they are used. I guess that's a benefit of stricter typing. And then they say that we have to provide an offset into each instruction line. So for the second line, we would have to provide an offset of 4 so that it actually breaks correctly. Yeah, then we get this nicer result in the bottom. The second to last update they provided is function context. This is an update that provides us with the option to store context during the basic block analysis. So it always has to be paired with a custom a basic block analysis. And then we can store context information for later use with updated APIs that use this context later. This is helpful for get instruction text and lift function to deal with certain problems we otherwise would have because we are missing information in these later parts. When we analyze the basic blocks, we get a view on the whole function. And for the other, for get instruction text, we only get single instructions usually, or at most a complete basic block, and that can sometimes be a problem. And for instruction text, we can actually pass fetch packet headers for our architecture, because they might be missing in our current basic block. And the SP loops also use multiple basic blocks, and the information, how many cycles we are iterating is in the first instruction and not in the subsequent basic blocks, so we can store that as well. And for lifting, it's also very helpful because we can store which instructions are pending into another basic block. Let's look at an example what we can do with that. The above is if we have the the architecture, and we try to guess how to translate, how to disassemble each instruction. But sometimes we will encounter instructions that would actually be compact. As you can see, it tried with a 32-bit instructions, and it was not valid. And the second difference is the SP kernel instruction at the end of a loop. That would usually have 2 parameters, but we can't split them up because we need the parameter or the operand of the SP loop at the beginning to split it up. And both is information that we can pass in this function context, and then we can just look it up later, and then it translates fine. So we have 2 compact instructions and 2 operands for the SP kernel instruction. Then one last part, the lifting. What can we do there? And there is one last update that Binary Ninja or Vector35 provided, and that allows us to lift whole functions at once. So again, we have full control over lifting. And in this case, we get the result from basic block analysis. So we get a list of, we had the signature of that function here. So we get a function lifter context that includes all the basic blocks. And the low-level function, as you remember when we, or may remember when we talked about translating single instructions to intermediate language, then it was called differently, but it was also this low-level IL function that we get passed. And now we want to lift, and we do this by handling each basic block and translating it as we see fit. And we can now also decide which shared information we need, which shared context we need to translate each block correctly, so we can freely pass in information, in and out information to translate instructions that are pending across block boundaries. And what would be a good approach, or what was the approach that I chose to lift the C6x architecture? Because the DSP executes parallel, we need to serialize that to low-level IL, because the decompiler expects serial instructions. And we can only do that, or I know no better solution than to split each instruction up into multiple parts. For example, for each instruction, we split it up into reads, then the computation of each opcode, and then writing back the results. So we again have a loop that handles each execute packet at a time, and we first split each instruction up and queue the parts for the cycles where they apply. And then we translate one cycle to low-level IL. And we start with reading, for example, condition registers and inputs for the current instructions. Then we translate instructions that have every input available. Afterwards, we write back results of completed instructions. And if we have branches that execute in this cycle, then we apply them in the end, because when we apply a branch, that ends block translation for this block. So we want to do that in the end. So if we have pending things we want to translate before, then we would add that before actually adding the branch. And with this approach, I had a problem with one specific instruction. This is an instruction that simply adds a 16-bit constant to a register, nothing complicated. But I relied on the output of my disassembler that also provided information about the access types and the cycles where these accesses occur for each instruction and for each operand. And I took this information from the specification or from a machine-readable version from libopcodes. And my lifting depended on this information. And it was sadly incorrect for this instruction. As you can see, it says that we read a constant, which is not really helpful, because it is encoded in the instruction, what we would actually need to read is the destination register that also contains the source value. And this is what I had to change then to make this instruction work in lifting. And then let's look at one other thing we can do now with the custom lifting. And this is a branch that is delayed across block boundaries. And in this case, we actually have two different blocks that queue the same branch in two source blocks. In this case, calling memset. And because it's delayed, it will only execute in another block. And you see a lot of temporary registers. The important one is the temporary register 101. The registers above 100 are used for temporary registers that are used globally unique in a function to pass values between basic blocks. And then the two source basic blocks can share this temporary register to pass the target address to the target block. And then when we look at the result in a higher level IL in the end, then it actually translates that to one memset call, which is what we wanted. There are a lot of topics that we could go on with, but it's probably also quite a lot already. This is just a small list of things that are not solved with this. And one last thing, I used a lot of examples from one binary. Actually, this binary has an empty main. And we still had all the examples we needed because the compiler kindly added some static functions into it. And they already used all the architecture features that I needed and have more edge cases that I would like to talk about. Okay, so thank you for your attention. Thank you for listening. And if you have questions, now is the time.
Thank you very much for this amazing talk. Are there any questions? Yes.
So you mentioned that Vector 35 actually was quite, or not far behind you in pushing out all these updates that helped you with correctly implementing your plugin. Were you actually involved with giving them the idea for those improvements, or was that just by happenstance?
I guess kind of. I mean, I couldn't have done without these updates. At least I wouldn't have been able to correctly hook these parts into the API myself. So it's very helpful that they did it. Before I really started to develop my plugin, I opened an issue like this thing is not working, and I was informed that this is a duplicate of a 5-year-old issue, and they then actually started working on it. So that is very helpful. I was not the only one asking in a short time frame, and then they decided to solve the problem now. I was in contact with them via their forums, and I told them that I was working on this architecture. Actually, now, since fall, they are working on the same architecture as well, because it seems to be a good test case for testing if everything works now. And I was also informing them about a few things that didn't work. For example, this function context is motivated by me telling them that my disassembly is breaking, because without fetch packet headers, I got basic blocks that were correct, but were missing instructions because I didn't have the fetch packet headers. So yeah, I was in contact with them. Some of the changes are probably motivated by that.
how did you settle for or how did you stumble upon that architecture? So I'm aware a friend of yours suggested it, but I think it seems to be a bit of an exotic architecture. And are you also aware of any, or do you also have hands on any hardware actually using that architecture?
Unfortunately, I don't have any hardware that actually executes that. I don't have many examples as well. So if anyone of you knows someone, or if you use this architecture, I would be willing to discuss it. For now, every example I had was built by myself, and it was just this one example from a friend that started it. And actually, I was later told this architecture was chosen because there was no tooling for it. So it was a reason to actually choose this architecture. Yeah. I mean, it's still sold. The CPUs are still sold, so I guess they are still used, but it's hard to find information on that.
You mentioned you had to translate instructions, basically. How many in total were there to translate? Like,
I'm not completely finished. I hope that you didn't expect that everything is working now. But there are, I mean, reduced instruction set in this case means I think it's somewhere below 200. And a lot of them are quite similar to translate, so it's just copy-paste for some of them, and then there are a few that are more complicated, and I spend a week on translating them correctly.
Okay, thank you.
How restrictive are the branches in the architecture? Like, what happens if some compiler decides to emit a branch that jumps into the middle of what another code path would consider an execution packet?
That is explicitly allowed, unfortunately. They mention that we are allowed to branch into an execution packet. I never saw it happen yet, so it seems their compiler is not using it. I only know of their compiler that actually uses this architecture well, because the tiny C compiler more or less doesn't use any architecture feature. The only one it uses at all is delayed branches to write the return address while the branch is pending. So yeah, I guess their compiler uses most of the features, and I hope their compiler is more or less sane.
Thank you for the presentation. I think like a lot of paradoxes can arise from the nested branching. For example, like the single knob basic block you showed. Like if there was another like nested branch thing situation where the second branch would jump to a different location, is there a way to like represent that in the decompilation? Because I imagine the knob basic block might already exist, so how would then like the decompiler deal with that? Do you like support that, or did you ever see a compiler do that? Or do you understand what I'm saying?
Maybe you will need to repeat parts of that.
Yeah, sorry.
But let me start a bit. I currently assume like every time I encounter a case where multiple branches are pending, when one is applied, I store these pending branches for the target blocks. And then later I compare that I always have the same set of pending branches at the beginning of each block. So if there's, for example, multiple sources that branch to the same target block, I currently assume that they will also queue the same branches. So if someone changes that, I will need to change my algorithm because I currently can't handle that. I didn't find that yet. So maybe that's something that's in most cases benign. Do you want to add on? Is there something else you were interested about?
Yeah, I see. So you did not see the compiler like doing a different second nested branch inside a basic block, and you assume
Currently, there's one thing that I know of that is currently still broken. I found an example where the compiler actually, I've talked about conditions and that we need to track them correctly to track the branches in basic block analysis. And I found one example where the condition values were moved between multiple registers, and that's something I currently do not handle, and then the analysis does not work. But the nested branches otherwise would work. I guess I just need to update the condition tracking.
Cool, thank you.
Any other questions? We've got a bit of time left. Oh, yeah.
Regarding the disassembly, are you using some disassembler you found somewhere, or are you disassembling the instructions yourself from the binary?
I mentioned it shortly. It's currently a disassembler that I wrote myself, which is mostly a Python port of libopcode's disassembly. So libopcodes also supports disassembly of the architecture, and apart from the one thing I corrected for this add-k instruction, both results would be equivalent. I just chose to write it myself because then I could choose the interfaces and the data types I get as result.
Can you talk about how bad medium-IL and high-IL currently looks?
Yeah, I guess it's. I'm not sure if I can show that on screen again. I will probably have to move the result. Yeah, the name is also like I had to. The version of the compiler didn't work the way I wanted, and I couldn't create a project, and then I was annoyed. So this is disassembly, and then we can go to pseudo C or high level, I guess. It already recovers the function parameters, and we do get loops and if else structures. But as you might see, they share conditions because in low level IL, this is the conditional instructions that I am currently still translating one by one. And that's a lot of if-else statements in high-level IL. That's something to optimize, I guess. But this is also the function where, in the end, we get this one memset call with two sources. Oh, and there's things broken, I guess. You see that in memset, a lot of things are not translated yet.
We've still got time for a short question. This one. Okay.
Okay.
Then
you have the plugin is available publicly. I will try to get it approved for their Binary Ninja's plugin manager as well, and I will try to make it more readable over the course of the GPN. Yeah, currently it's somewhat a mess.
Still 2 days left.
Yeah, I guess. So, yeah, you can find me with the CTF team. We have a table near the merge desk that is we will probably find it because it is decorated, or there were contact information on the slides as well.
Thank you very much for the talk, and a big round of applause, please.